So, can we tell what this is? This is one of the earliest examples of combinatorics, magic squares. Combinatorics is an ancient field. Its history may be traced back over 4,000 years to the age of the Great Yu. According to the Chinese myths, the Great Yu tamed the Yellow River. There is a legend that says, while working to tame the river, the Great Yu was very worried. One day, he was strolling by the riverbank when a giant tortoise rose from the Yellow River. This tortoise was not only huge, but even more amazingly, there were mysterious patterns on its back. If we study the patterns carefully, we discover that its back is divided up into 9 squares. Each square contains a number of dots. If we add up the dots of each row, or of all columns, or even of each diagonal, all adds up to 15. 15 is quite a special number in the Chinese lunar calendar, since solar term lasts 15 days each. So the Great Yu was inspired by this mysterious pattern and divided the work accordingly into 15 days period. Magic square appears not only in the ancient literature, but even in well-known works in film and television. They appear frequently. Next, we will watch a short clip from the legend of the Condor heroes. Yinggu, who lived in the cabin by the Black Swan, was studying how to form a 3x3 magic square. Yet over a decade passed, and she still could not reach a perfect solution until Ronghuang came to the cabin that was.
算法自然经我100倍，可是我问你，将1至9这9个数字分成3列，不论纵横斜角，每3个数字相加都是15，如何排法
？9宫之意，法以灵归，2、4为间，6、8为足，左3右7，带9履1，5为中间。
知道，这是我独创的秘诀，没想到却早有歌诀传世。
那9宫每宫又可化为一个八卦，8、9、72数，以从1至72之数环绕9宫成圈，每圈8字。 交界之处又有4圈，一共13圈，圈圈相加均为292。这洛书之图之中的神妙，想必你也不会了解。
So is it really as commonplace as Ronghuang says? In fact, the first person to investigate magic squares should be the mathematician Huiyang from the Southern Song dynasty. In China, Pascal triangle is actually named Huiyang's triangle. Aside from this, he authored the very interesting mathematical treatise Classic Algorithm. Within, he detailed 3x3, 4x4, 5x5, and even 10x10 magic squares. So, as we can see, apart from the 3x3 magic square found on the tortoise, there are many much larger magic squares. Western mathematicians, too, delved into the secrets of magic squares. There was even a famous engraving named Melancholia 1. In the top right corner of the engraving, there is a 4x4 magic square. Let's examine carefully this 4x4 magic square. In the 2 squares in the middle of the last row, one holds a 15 and the other 14. This demonstrates the cleverness of the artist, for this engraving dates back to 1514. So, it can be seen the secret behind the order in magic square are almost beyond the imagination of mankind, and some feel the magic square harbors secrets of the universe. For precisely this reason, in many religions, magic square hold special symbolic significance. Even within their temples, magic squares are carved onto the walls. So, if we are to study magic squares, we must first give them a formal definition, a prerequisite for any rigorous mathematical investigation. First, we must have a n by n grade. Shall put the number 1, 2, 3 all the way up to n squared into the n by n grade. We must guarantee that for every row and column, and even for its diagonals, the sum of the relevant numbers are identical. So, for a magic square of arbitrary size, in order to study it, we must first calculate the sum on the rows, columns, and diagonals. So we define the sum of each row and each column and each diagonal to be the magic sum. Let's denote this sum by the lowercase letter s. Then, for a magic square of size n, if we wish to calculate s, well, what's the sum of all the numbers from 1, 2, 3 all the way up to n squared? There is a formula for this. The sum of 1 plus 2 plus 3 all the way up to n squared is equal to n squared times n squared plus 1 divided by 2. But this number is precisely n times s, so the magic sum of the magic square is equal to n squared times n squared plus 1 divided by 2 and divided by n. Now, for a magic square of size n, we know the magic sum should be equal to n times n squared plus 1 divided by 2. Since for every natural number n we can calculate its magic sum, then it is true for all n that we can just arrange numbers from 1 to n squared and put them into an n by n grids to form a magic square. Let's use a simple example of when n equals 2. Does there exist a magic square of size 2? How do we put the numbers 1, 2, 3, 4 into a 2 by 2 grid so that the magic sum of every row and column are identical? We first assume there does indeed exist a magic square of size 2. Then the following must be true. Let's use letter A, B, C, D to denote the entries in the grid if there exists a 2 by 2 magic square. What its magic sum should be? Substitution into our formula reveals that the magic sum should be equal to 2 times 2 squared plus 1 divided by 2, which exactly equals to 5. This means that in this configuration of A, B, C, D, horizontally A plus B should be 5, the second row C plus D should be 5, and diagonally both A plus D and C plus B should be equal to 5. But now we spot the problem. If we take the difference between C plus B and C plus D, we obtain this result, B minus D equal to 0. However, we know that the four numbers we picked are each distinct and cannot be equal to one another. This is from the definition of magic square, so we have a right and a contradiction and our assumption must be false. A magic square of size 2 does not exist. But just now we have seen examples of magic square of size 3, 4, 5, and even 10. So what is the real answer to the question of existence? In fact, roughly 30 years ago, a German mathematician proved that it is always possible to construct a magic square of size n for every n larger or equal to 3. Since magic square exists for n larger than 2, we quite naturally wonder, how do we construct a magic square? Actually, Hui Yang introduced in his book a method of constructing a magic square of size 3. He first arranged the number 1, 2, 3, 4, 5, 6, 7, 8, 9 in diagonals. Then exchanged the numbers on opposing corners, finally forming a 3 by 3 grid. Thus, the result is a 3 by 3 magic square. But this method is only applicable to 3 by 3 magic squares. It was only in the 17th century did a French mathematician discover how to construct larger magic squares. Of course, his technique had its own limitations. He could only create odd-size magic squares. What then? What his approach? In fact, he first imagined an n by n grid like this. To not be flat, he filled the grid up in a fashion akin to going around the globe. At the same time, when he places the numbers, he always goes from bottom left to top right. Next, let's demonstrate this method with a 3 by 3 square. Next, we will use this device to introduce to everyone the construction of the 3 by 3 magic square. The first step in the method is that we put a 1 in the middle of the first row. The process goes like this. If we pretend we are moving a piece from the bottom left to the top right, but during this process it might be moved out of bounds, we can make further progress by pretending the edges are conjoined. Going off one edge meaning coming onto the opposite. Simply moving the piece of its second position will cause it to fall off the edge of the board. However, since going off one edge meaning coming up to the opposite one, it should actually arrive in this position, so 2 should be placed here. 3 will be in the next position. If the opposite edges are also conjoined in this direction, then 3 should be placed here. According to the rule of moving from the bottom left to top right, we find that moving to the next position from 3 will cause us to move to where 1 is. Now, this is special case. If the next position is already occupied, or we placed the piece immediately below the previous square. Therefore, 4 should be placed here. After this, we try to find the positions for 5 and 6 following the rule. We don't have to do anything special until 7, when the next position will go off the board. By observing that 7 will be placed at this position in the corner, which is already occupied, so we must move to the square immediately below the previous square. Next, it's time to find the position of 8 from 7. We see that it should be here due to the conjoined edges. Finally, our last square is reserved for 9. Thus, if we now verify the sum, 8 plus 1 plus 6, 8 plus 5 plus 2, the sum of any row, column, or diagonal comes exactly to the magic sum of 15. Since we know how to construct odd-sized magic squares, then everyone must be wondering whether for a magic square of arbitrary size, there is a corresponding method. In fact, we can divide magic squares into 3 classes. The first class comprises odd-sized magic squares, the second magic square of size 4 times m, and the third magic squares of size 4 times m plus 2. Each class has its own method. So by now, if we are given any n, we can construct a corresponding n by n magic square. But if we go back to the earlier 3 by 3 magic square constructed using Hui-Yang's method, when we compare it with the magic square we just constructed, are the two the same? At first sight, these two arrangements are different. However, a careful inspection reveals that if we rotate this magic square, we obtain 2 identical magic squares. That was a 3 by 3 magic square. Let's now move on to a 4 by 4 magic square. Here is a magic square from the engraving. This magic square we are seeing are carved next to a temple, although they are both 4 by 4 magic square. No matter how you rotate or flip, their arrangement are not the same. This leads to the question, if we take a magic square of size n, how many distinct magic squares can we generate? In fact, the counting of magic square has long perplexed people. We know that no magic square of size 2 exists. If discount flips and rotations, then for a 3 by 3 magic square, there is only one possibility. Once we are up to 4 by 4, there are 880 distinct arrangements. If we allow for flips and rotations, there are 7,040 possibilities. For 5 by 5 magic squares, we can all imagine how many 5 by 5 magic squares should be. There are already over 270 million 5 by 5 magic squares. Exactly how many 6 by 6 magic squares should be is beyond our ability to calculate. Even computers are incapable of enumerating all possibilities. Mathematicians determine that it must be within a certain range, roughly 1.77 times 2 times 10 to the 19th order. What about magic square of size 7? No one really knows. Even the range in which it lies, we don't know. Thus, we can see how difficult counting is. So, is this the greatest extent of research into magic square? Already, we have only come across ordinary magic squares so far. There are many other forms. We can consider an arbitrary number sequence. Neither do we need limit all the numbers to be consecutive sequence, nor do we have to use ordinary numbers. We can even put various prime numbers in the grid to construct a magic square. Some people have even said, okay, the sum for each row and each column is identical. In fact, there are a number of people trying to form magic squares where the product of each row and column is identical. This also makes for a special form of square. Magic squares are so great. They are attracting the fascination of the world at large. In the year of 1977, magic squares as a symbol of the intelligence of mankind were transported into the space. At the same time, I found the elegant construction like magic square in fact also offers special way of expressing yourself. In fact, during the year of 2008, a headline attracted my attention. A 17-year-old farmer designed a very elegant magic square. It is a cube, where its every diagonal and even its every row and column each add up to equal 2008. Unfurling this cube onto a plane produces a heart-like shape. Moreover, at each corner, take the sum of 5 numbers in a cross and subtracting the number on the opposite corner is exactly 2008. So Mr. Zhong Xiangbao spent 3 entire years designing this perfect magic square to honor the Olympics. The development of magic square allows you to let loose your imagination. The study of magic square is both rich and profound. In combinatorics, there are many similar sophisticated structures. Just now, we covered some of the development of combinatorics in China. We must be eager to learn more regarding the West. How did combinatorics begin and develop in the West? So, in the next lesson, we shall begin a deep discussion about the development of combinatorics in the West.